still need to do the pointer here. Yes, okay, so the title I was given is the NOMAD Project. I in fact gave it a subtitle. Oops. A subtitle, Turning Data and Information from Computational Material Science into Knowledge by Artificial Intelligence. I'm not sure actually why this arrow is there. Okay. Now, we already briefly mentioned last time that if you have a lot of data, there is information in data which you may not see otherwise. And that brings us to what people now call, and actually also we call, a new paradigm in materials research. And my talk essentially really talks about or deals with this new paradigm, telling what it is and how it can help us to develop new insight. I will not actually repeat what I said before, but it's actually the same slide. I only want to say that we now focus on number 4, big data-driven science. So if we have big data, we are able to identify structure or patterns in data which we would not be seen if we would look at, say 2 or 3 or 5 measurements or theory calculations. And in fact, what we also think is you would see correlations, or you see patterns which you would not be able to easily analyze in terms of scientific laws, because some relationships in science probably cannot be described in simple ways, because there's so much intricacy, so many things happen together. And I'm working, for example, in heterogeneous catalysis. There are molecules coming to the surface, but you don't really know how the surface looks like. There's dissociation, there's hopping. There are so many arbitrary things which can happen. Altogether, things is happening in some describable way in terms of seeing some rules or some structure, not necessarily easy rules. And this is what we want to identify, and given up really the need that there is an easy a law behind it, because there could be actually several laws very intricate behind it. So giving this up, but not really saying actually, I mean, maybe there is one, and we'll find this later. That's also actually very good, but not necessary. So learning from big data means, in fact, there are many methods. There are many concepts, and that's what I felt makes it very interesting. I mean, I worked for my whole life on electronic structure theory, basically DFT basics, and also say excited states to some extent. But it's a completely new field, and it's very interesting because there are also very new different concepts. There is one, say, how you say that, some umbrella expression which we call, or which is called artificial intelligence, which in fact means learning from experience. I feel this is in fact really the best umbrella term. There are other expressions which nearly are as general as this one. One is is big data analytics, and somehow in my talk probably very often I will either use analytics or this one, or in fact there's also machine learning, where I feel machine learning is a little bit narrower in the sense that machine learning is usually meant in learning from data. Learning from experience in fact acknowledges that there's not only data, there's also other information which we have, and for getting insight you need to use everything. You need, if you do machine learning, I would say you need domain-specific versions of machine learning to achieve a good understanding. And you'll see in my talk what I mean, what is needed in material science for that. So that's why I prefer a little bit the artificial intelligence, but it's essentially the same, using the other terms as what other people use in the same way. As I said, actually, it's a very general, very wide, and very interdisciplinary topic. You see concept of that in chemistry, in informatics, intelligent systems, robotics, data mining, clustering, bioinformatics. In fact, a lot which I'm talking today comes from signal processing, which initially has nothing to do with machine learning or artificial intelligence, but the way we are developing it and using it in fact, it now has. So signal processing or data compression are very good tools in terms of artificial intelligence in the way we think one can use them. So everything which I'm having here will play a little bit of a role during this talk. The methods which are used, one which probably is the oldest one in this field is neural networks. Neural networks have been invented something more than 50 years ago, but in mathematics, but have not been really very much used because people actually, there was still actually a lot of development necessary, and of course more understanding for what you can use them. Another very powerful method is support vector machines, kernel-rich regression, Gaussian process, decision trees, compressed sensing, and so on. You will hear some of these later again, and I tell you about these during my talk. So it's a lot of different methods, and that makes the field so interesting also to be in this and to learn. Now, if you deal with the big data, or if you specifically maybe in our field, computational material science, and which then would be called high throughput computations. People from computer science immediately tell you, and you realize it yourself, there are 4 challenges which are typically called the 4V. V means the volume. So you have to deal first, before you can do the science, you certainly have to deal with these things. You have to deal with volume, the amount of data, variety, the heterogeneity and of form and the meaning of the data. Right? I mean, data is interesting, but if you have no idea, no tag, no label, what it really means, it's a big problem. Velocity, at which data may change or new data arrive, and veracity, the uncertainty of the data quality. In our field, the main challenges, I think, are with variety, the heterogeneity of data, and in fact with, I was too fast, but doesn't matter, with veracity. Now, once you have solved that, then in fact you can deal with what I will concentrate in my talk, the big data analytics, which in my previous slide I called, in fact, artificial intelligence. Now, big data analytics means acknowledging and using that big data of materials has structure and patterns, and that means correlations, and we want to use and understand the correlations to get better insight. So the dream is that there is structure. And if you would know, so you don't know, but let's just assume you would know the descriptive parameters which are relevant for what you are interested in. So let's say there is a coordinate x, or actually d1, one descriptive parameter which we don't know yet, another descriptive parameter which we don't know yet. Then your data will somewhat cluster. There will be an area or a region where data tell you in this region the systems are good sensor material, or in this materials. In this region they are good transparent metals and so on. So this is the idea. Can we put all the many materials which we have in science, can we put this in these type of areas like a map that we say, if you are looking for a better or certainly for a good superconductor, this is where you have to search for. Now, these areas are very small. They look big on the screen here, but in fact, if you just think how many data we know, we already know about 300,000 how many materials we know, that 300,000 materials exist. Now, when we say that 300,000 materials exist, that means they exist, they have been, the structure has been determined, but we hardly know anything about it. We don't know if they are metals or semiconductors, or are they transparent or whatever. We don't know if they really belong to this class. If we then ask how many materials exist of a certain function, so for example, how many materials exist which are, say, have a very high transparencies, at the same time have a very high heat conductivity, and how many, and at the same time are scratch resistant, then you're actually down to probably actually less than a handful. It's diamond which is really the key materials doing it, and there's nothing coming close to diamond. So you have an infinite number, practically infinite number of materials, but there's only one or two which are really having the function. And of course, when you talk about functional materials, and material science means in fact having a solid or a material which has a function, and you've talked with people from engineering, you have these conditions that the material should do something. It should be good for photovoltaic and so on, and very fast from this nearly infinite or practically infinite number of possible materials, you are down to very, very few. So these areas which I'm showing here is very, very small, but finding really, identifying this this region, and that means identifying these descriptors, the X and Y axis, this is the big challenge which we hope we can solve with big data analytics. In this aspect, we also have to think what big data really means. I mean, I just told you, if I'm looking, I have big data, right? I have big data, I have an infinite number of materials. But there's only one material which has a good scratch resistance and a good heat conductivity, and this is diamond. So at the end, it's actually not big, it's just one. So you start with an infinite number, but you can also say, from this infinite number, most is irrelevant. So irrelevant data will not help you for finding what you're interested in. So you have the problem that big data is really a problem, that big data could mean actually most of the data are not very relevant. But in fact, to identify things means you have a complex situation, and therefore big data also means a big number of options for a description. What should we really use to find the descriptors? And of course, there are so many possibilities in solid-state physics, so many processes, so many mechanisms. You have to really scan all of these possibilities to find what are the descriptors. And so I think the issue is largely the number of options which we have to identify the structure in big data or in data, than rather that we at the end will find that many data will have this function. Now I wanted to talk first about variety, the heterogeneity of the data. And for this, it's just a historic remark to some extent, that started with the NOMAD, or in fact, which later became the FAIR data principles. What we realized, and we means actually Claudia and I, 5 years ago, we realized that a lot of people are doing good theory or good measurements. So we are computation, so let's say theory. People are doing a lot of calculations, but everyone is keeping these calculations for herself. It's a zero type of this. So this is my thing. I don't really like to show. I do a calculation which sometimes takes 1 million CPU hours, and then I publish 5 numbers. But there's so much more information behind that. And if you could offer that would be a big advantage or big help for many people in science. So we argued that we need extensive sharing of scientific data. And of course, sharing means you must present data in a way that they are findable, that they are accessible by others, interoperable, and repurposable. So we use the word repurposable, other people. So in fact, so this was identified, or the concept of NOMAD. FAIR is this acronym which you just see, right? F-A-I-R. Came a year later, they actually used reusable. We still prefer repurposable because it describes better what we really want. We want that if someone has done a calculation, right? I mean, one thing is you just want to check what has this person really done. Is it necessary that I do this again? I mean, there are thousands of calculations which have been done again and again without any need. So yes, you want to check, why do my calculations not agree with the other ones? Very often, in fact, it's your mistake or my mistake and not the other ones, but the first idea is usually the other one is guilty. But so it's good actually to check what has been done. But in fact, you can also use calculation for something else. People, for example, the key example I'm always using is titanium dioxide. Titanium dioxide is used, for example, as I told you, I'm doing heterogeneous catalysis as a support material in heterogeneous catalysis. You use titanium dioxide and then you put some nanoparticles of the catalyst on top of it. There's a lot of calculations on titanium dioxide in this field. But in fact, with respect to catalysis. But if you would have all the information, you could use the same information for other fields, because titanium dioxide is also very important for photovoltaics, for the so-called hybrid organic-inorganic solar cells. And it's actually very important in pigmentation. The sunscreen white or the toothpaste, the white is titanium dioxide. If you have all the information, you can actually you do it for a different purpose. And so that way you felt actually repurposing is what you want. Reusable sounds like a used car, which we don't really want to. But it's the same idea which is behind that, using the things which are there for something else. So that's what we started, Claudia and I, in 2014. It went really online, and which is called the NOMAD repository. You can look at it. So it is at YouTube, but in fact we are also now very strong in China, and you know China is banning some things. YouTube is banned in China, so you have to look at UQ, but it's the same movie. So the idea is that people really should upload their files, and the idea is also to make it easy. So when I said it should be findable, accessible, and all this, if you just request that the people who do calculation have to worry about this, it will not really work, because it's an additional step. But in fact, the other thing which is nice in having such a repository is not only that you help science and you give other people the information. If you are like me, actually it also helps yourself, because after 2 years you also don't find anymore what you have really done, or your professor doesn't find it anymore. So it also helps really the group to organize things and uploading it somewhere, and that was certainly also one aspect. But of course it helps science significantly. Now, we wanted to help the whole field, and that comes again to the heterogeneity now. The field in computational material science is very diverse. I mean, there are many computer codes. And so we realized that we have to serve, or we should serve, something like 40 different computer codes. 30 codes we are serving is from ab initio calculations, the things which you are learning. But actually there are also 10 which come from force fields or molecular mechanics, like lamps and chromax and whatever these things are called. This is all what our field is doing. And what you see here is the statistics of total energy calculations, which now have been uploaded to the NOMAD repository and archive. In fact, when we started in 2014, and we wrote actually the first proposal, I made an estimate that by the end of, say, 2018, we probably have something like 100,000 calculations which people have uploaded. But because we also realized there was some resistance, and actually there's still some resistance. Some people don't want to show everything, because why should Pasquale get my data? I mean, he's publishing something nice with this. So there's still actually very few people who are reluctant in doing it. But in fact, the success was enormous. It was really a change in culture, how you do science. And now we have actually not 100,000, we have more than 50 million total energy calculations, which in fact brings us also in some problems that we have to restructure and just going through the whole data file system. But that is actually nice, right? So here you see a little bit of the statistic, what codes are the most present. So as I said, we have altogether 40 different codes, but these are the most important ones. There's a Wien2K, WASP, is in fact the leading code. So this is the logarithmic scale. So don't forget it. There's really huge numbers. So WASP is the leading code, but you also see Gaussian, FHI is our code from the Fresava. Here you see exciting, and UpInit is also a very well-known code in our community. So you see a lot of codes are there, very different codes, plane wave codes, pseudopotential, all electrons, and so on. Now, why is WASP leading? The reason why WASP is leading that is somewhat very simple, because we also succeeded, which we did not expect, I have to say, to convince our colleagues in the USA to join. Now, that was nice. In fact, that didn't need any work. I mean, they just liked the idea and felt it would be nice to contribute. And so, in the US, this Materials Genome Initiative started first, right? This was an initiative by the White House, by Obama, many years ago. And they are all, to some extent, using WASP. And so 90% of this big bar is really WASP calculations, coming from the database of Stefano Cottarolo, AFlow, or from Chris Wolferton, OQMD, or these are, I would say, the initiators of the whole materials project, or materials genome project even, idea, Gerd Zeder and Christine Persson. They're all here. And in fact, what we are now doing is that they realize that the synergy is working so nicely. So for example, if you want to have, so what they are offering on their websites, which you I guess also use maybe once in a while, they are offering something like an encyclopedia, like what Claudia will present later in our view. They just look for very specific things and doing the physics with the data, but they don't really offer the input and output files directly. And so if you want the input and output files from OQMD, in fact, you are told, please go to NOMAD, and then you will find them. So the collaboration and synergy works very nicely with these colleagues. So this is the entry level. So the first thing we felt we need sharing, and that is the repository, which in fact is opposite, or it can actually, it's not opposite, it's orthogonal, I would say, orthogonal to everything else. It's not really a standard database. All other databases are a very small user group, and they're usually just using one code, the WASP code, which I just told you, right? Then everything is easy. But we said actually we're not really one user group. We want to be open to everyone. There's no barrier to upload, and there's no barrier, even less barrier, to download. And we are different that we accept, in fact, I would say actually we request. So if you want to join and send something, you have to give the whole input and output files. As I said before, in the beginning, people just felt, okay, I can give some result, right? I mean, I publish a figure and I give you the 10 numbers behind the figure. But I don't want to give you all the details. But we requested we want everything because other people should have all the information. And as you just said, now we have more than 50 million. So what is a type of an incentive why people are doing this? First of all, when you have uploaded, the NOMAD repository keeps these data for at least 10 years. So you also don't have to worry anymore that you don't find them. And when we say at least 10 years, it means at least it keeps it for 10 years after the last upload. So at some point when we say actually we don't want to run this anymore, then actually we don't accept uploads anymore, and then it will be still 10 years. But if you are there already since some years, of course for you it's longer then. But at the moment there's no sign that we'll stop this service. Things are open access, but in fact if you want open access with delay, because we also understand you want to collaborate with people, and maybe you want to upload your data, but you want to share it only with 2, 3, 4, 5 other people. Upload with delay is possible, and you can delay up to 3 years. So it's a long time. You can finish your work, but after 3 years the thing will be published or open access. In fact, when we said actually we have more than 50 million, I should actually say 50 million open access total energy calculation, because there are many more, which then of course over the years will become open access. But we don't look at the known open access. We really keep this even on a different hard disk to make sure that if someone wants it not open access, this can be done. In fact, this open access story is also interesting, that we also offer so-called secret user IDs that if you have a publication, you can tell that a referee can look at the data. So if a referee wants to see how good are the data, she or he can look at it by this thing. They would not look at your website, because then they can be tracked, but of course looking at NOMAD, they are certainly anonymous. And of course we provide DOIs, digital object identifiers, which means the data can be cited. So if people publish or you publish, you give a DOI, and immediately people have access to the data. Again, okay, so this is somewhat the entry level, which is nice and very important to help the field who's doing the calculations, but it was not really exactly what we felt we want to do, because the problem, what we already mentioned, computational science. What is that? Okay, no idea. I'm apparently, for some reason, in the internet, which I didn't want. Usually I switch the internet off when I'm giving a talk. Actually, I'm off. I'm in the flight modus. Okay. Huh. Strange. Something new. There are always surprises, right? Okay, so we wanted a repository. But if you look at the repository, you have a lot of information, but because these are different codes, they come from different communities. They come from physics, they come from chemistry, they come from material science. They speak somewhat a different language. Chemists, when a chemist talks about a chemical bond, the person means something slightly different than what we need, or a spectrum, or actually an energy. If they talk energy, I mean, and of course units. I mean, they have kilojoule or kilocalories. We have electron volts or hartrees. Every code apparently is really quite different. And so the first thing which is necessary is to bring this to a common format. Now, in principle, many people, when we started 5 years ago, that yes, we should have a common format. We should really tell that there is a format and everybody should follow. I think it doesn't work, and I feel we have to do it the Chinese way. If you have a plug, an electric plug, I mean, if you're traveling in the world, you have a big problem. If you're in China, you have these things which fit where your plug fits wherever you come from, because you have a converter in the plug already. I think we need a converter, and I think we have to give the converter. And so we have a conversion layer which brings us from the repository to the normalized data archive. And this we then offer, and now people can use this for many services, like an encyclopedia, and you will hear a very detailed talk. What you can, this is somewhat, I call this the face of the whole thing. This is where can people see. This is now the material science view. You can look at, you can ask, where do I find a specific heat, or do I find a certain band structure, and so on. And Claudia will talk about it. We can do big data analytics. I tell you a little bit about this, but Maria will talk more, and you can do visualization, which we're not really talking, but there's also a lot of new things coming up in visualization. A lot of things you cannot really plot very nicely. I mean, you can plot in 2 dimensions and maybe in 3 dimensions in some way, but a lot of things are high dimensional. A lot of things which Lucia told you, you really only feel what an exciton is if you can look at it at 6 dimensions. So one thing we felt actually it would be nice if you have a VR, a virtual reality glasses, and you say, now I'm the electron and I walk through the crystal and I look where the electron is. Or I am the hole and I look where the electron is. So getting actually a better feeling about what is going on and looking at higher dimensions. And that's also what people in this project are doing, which is funny, but actually is also getting more scientific now. But it's a good thing to have. So this is actually what the whole project is, and I like to talk about more now about the concept of the analytics. Actually, no, I first wanted to talk more about the veracity, because in doing things you also have to be sure what is the accuracy and maybe the precision of your calculations. Now, I was lucky that I don't have to do this here, because Sven will talk about it, I think, today at 5:30. So there will be a special talk on veracity. Where are we in ensuring how good the calculations are, and of course, what else needs to be done at 5:30 today. So we want to do science with the data. And that is artificial intelligence or statistical learning or machine learning. And I give you one example, which is kernel-rich regression, because I feel this is the simplest one, but it has all the elements of the other methods in artificial intelligence tools. So the idea is that we have some data, and I call these P index I. So I tells actually how many. Say if you have 1,000 data, it would be 1,000 numbers P1, P2, P3, and so on. And we have coordinates, which somewhat lists what these data are. I mean, you have to identify them. So you could identify them. This was calculated on Monday, this was calculated on Tuesday, but you can also maybe have another type of description. And DI is a set of descriptive parameters, which in my plot, if you remember these clouds, when I said a cloud of different materials of D1 and D2, the important thing is what is the best descriptive parameter to see structure. Monday, Tuesday is certainly not a good parameter to identify science, but we need a descriptor, but we don't know this in the beginning. But assume for this slide that we would know that. Then machine learning is nothing else than saying we want to write down our properties as an analytic function, as a sum over initially unknown coefficients and a function which is called the kernel of descriptor I and descriptor k. So this function can be many choices, and I list some later here, but let me just say, so this is a little bit like a basis set representation. You have a lot of points and you want just to make a continuous curve through the points. And the way this is done in machine learning is that you say if you have 1,000 points, so you have point k equal 1 to n and n is 1,000, then you sum this with 1,000 basis functions and 1,000 parameters. Now, if you have 1,000 parameters, that should be possible to fit 1,000 points, right? So this is the idea. And then, of course, you have a fit of the system, and everything in between and everything which has not been fitted should be hopefully also be described well. The kernel which is used can be a linear kernel, which will be just a product of di and dk. It could be a polynomial, which would be just the product with some power. Or most often people use the Gaussian kernel. But this dk of di dk is just really a Gaussian. That means what you're doing here is a somewhat at least square Gaussian fit to the data. But where usually in least square fit you use 5 Gaussian, here you use as many Gaussians as you have data. So there is a general word in machine learning which says more data means a better description. And some people even identify machine learning by this phrase. Now, of course, our question is, do we learn anything? Now, if you really think about it, you have also to think, what does the word learn mean? Learn does not have nothing to do with understanding, but that's another philosophical thing. But that's another thing. I mean, the machine learns something. Do you learn something? That's a big question. And of course, you can do this, but for a good predictive power, will we ever have enough data? Now, for our field, in fact, I like first to question this sentence. More data means a better description. As I said, this is a general statement in machine learning and not really question. It makes a lot of sense. Somewhat it sounds plausible, right? You have a fit and you think actually adding more data, the fit which you have here should become better the bigger the n is. I like to point out this is wrong in our field. It's wrong because, as I said before, you have a fit, but you have actually certain focus. You want to identify a material which is certain, with a certain function. And adding data which are not relevant doesn't really help you. I mean, adding irrelevant data really brings you away from what you want to describe. And as long as you don't know what's going on, how can you add relevant data? I mean, this is the main problem in this whole field. Identifying what is relevant and what is not relevant. And the problem here is there are many subgroups in material science. There are certain systems which behave in one way, systems which behave in a completely different way. Let's say transition metal oxides, semiconductors, say sp3 bonded semiconductor, and so on. These are all very different systems. And just assuming that you can describe them all with the same thing, if you are interested in a transition metal oxide, does it really help to add silicon to the pool, or does it help to add something else to the pool? Right? In these systems, we typically do not have big data. At the end, when we are interested in the data, are not big. And what I'm saying when I said we have a lot of irrelevant data and very few relevant ones, we are looking for needles in a haystack. Right? There's an infinite number of possible materials, but we are looking only for 3, 4, maybe actually 50 or 100 in some cases. But sometimes I'm really sure that for when I said actually the best heat conductivity in scratch resistance is diamond, there's nothing close. So maybe actually there's only one out of an infinite number. We are looking for needles in a haystack, and somewhat the statement which I said that more data means better description is wrong, because I mean, it does not help to add more hay. To make the haystack bigger does not help you to find the needle. So that is what I think is why the standard way of machine learning is not helping the field which we are in. Let me tell you about one example which I want to use, and again the goal I'm having in solving this, what I just have said, crystal structure prediction. This is, I call this the toy model, but it's also a classical model in condensed matter physics. We want to do a classification. Can we predict? This is again the idea of building a map. Can we predict which systems will assume the zinc blende structure and which system will assume a rock salt structure? Zinc blende, you know, like silicon or zinc oxide, every atom has 4 nearest neighbors. Rock salt, every atom has I forgot, was it 6 nearest neighbors? I think it was 6 nearest neighbors. Yes, I should know this because I'm saying that so often. So it's really the number of neighbors is different and the structure looks very, very different. Is it possible if you just give me the 2 atoms that without doing a DFT calculation, I can get an understanding what structure this thing will have at the ground state? Now, if you calculate this for the rock salt semiconductors for binaries, so this is the nuclear number of atom A, the nuclear number of atom B. And the color code means full red means it's zinc blende, very strongly with a high cohesive energy difference. More open means still zinc blende, more open still. Green means the 2 structures are degenerate, and turning towards blue means it's turning towards rock salt. So this is the prediction which we have here. That doesn't really look like an easy map. Right? You want a map that you can say, actually, here is one and here is the other one. So what you really want when we talk about a map is something which looks like this. We want a descriptor, apparently ZA and ZB are not doing this, which tells us if you have D1 and D2 in this area, then it's zinc blende. If you have D1 and D2 in this area, then it's rock salt. How can I find these coefficients? Now, first of all, we need to arrange data such that statistical learning is sufficient, because again, when we see what statistical learning is doing, it's doing this interpolation. It describes the thing in terms of an analytic function, but an analytic function also means it should be a smooth function which you fit. I mean, if the thing has no structure, what does the fitting really mean, and is it still valid in between? So you first need to arrange it in some way before you can do a good machine learning thing. So this is, and that's why we have chosen it, a classical thing in condensed matter physics. Jim van Vechten, J.C. Phillips, and many others have worked on this. But in fact, what they have done in the past, they showed that, yes, this is possible. But in fact, they used for D1 and D2 properties of the final result. Right? I mean, they used the dielectric constant of the zinc blende structure, or they used the lattice constant. Now, of course, if I wouldn't know the dielectric constant, then I know actually already the answer. So D1 and D2, that's another request, must be simple. I mean, they must be related very closely to the nuclear numbers. They should not require a DFT calculation. Otherwise, the whole thing would make not much sense. So in principle, that's what the idea, how to find D1 and D2. And of course, I plotted in 2-dimensional, but I said already, there's no reason that science is 2-dimensional, and also not here. So we want also a formulation which is more general. So is this really possible in general? And my answer will be, probably this is not possible, but it is possible for subgroups. If you have this infinite number of materials, and first, in fact, you identify, and again, this is what artificial intelligence should do for you, you identify subgroups. In the subgroups, you probably can do this. But in general, we believe you probably cannot really do this. But again, what do I mean by this? So again, a concept in artificial intelligence or machine learning, going in the same direction. What people usually want is what they call, or what is called global learning. You want to learn everything with one type of method or one type of model. And I already told you that I believe doing everything with the same model, because of the way condensed matter physics work, is most likely not working. And we have several examples actually that it does not work. But still, what is global learning? And I just wanted to do this in a tutorial way here. So a global learning in general means you have a population. That means you have a certain type of materials. And from this certain type of materials, you have samples, and these are this is just an example. I don't. It's more in academic examples. You have 900 points, and for these 900 points, you have an x coordinate and you have a property which is y. So this coordinate x somewhat is the descriptor which brings us from the property somewhat to the related y value. And the model which we want to use for machine learning should bring us from x to y. The way it's done is we define a certain model, a certain function. You have seen the example of kernel-rich regression. That is one model. And we request that the error of this model compared to the data which we know, that this error should be low. Now, there's one thing which I have not said. I have said actually you want to do this fitting. You want that the data are fitted by say 1,000 Gaussians or so on. That is a mathematical problem because that brings you into what is called overfitting. It will not really work very well. You need to have another requirement because you want that the result is a smooth curve. That means you have to add what is called a regularization term. The regularization is what is in fact here. So you want to get the best fit under the condition that everything is smooth with a certain error bar, and that is indicated here by the norm of this model, whatever the model is. So what could be one model? One model could be a linear fit. You say, I have my data and I want the best linear fit. So if you do with the data which I had, the best linear fit is the black line here. And then you say the error bar, say to have actually 65% confidence are these dashed. So that means I have an x value and this would be the prediction with a certain error bar. I mean, the error bar is huge, as you see. And the question, of course, is do I learn very much? But the nice thing, at least in this treatment, is you have only two parameters. One is the slope and one is the value here. And so in principle, you could say, actually, can I learn something? But then if you see this fit, you would say this doesn't really look like a good fit and good insight. But that is how machine learning would do this. It would actually say, I'm doing the best fit. I use my kernel, and here's a linear kernel. What would I get? Now, a little bit more sophisticated is using the Gaussian kernel. So with the Gaussian kernel, the best fit of the data is the black curve here. And the errors are again the dash curve with 65% confidence interval. Now the error bar is somewhat smaller as before, so the fit is much better. But of course now the interpretation is a problem. Because to interpret this curve, before we had only one number or two, now we have actually 1,000 numbers. Now, what is the physics if you have 1,000 numbers which fit the data and you have in 1,000 numbers? It's just a mathematical, it has no zero insight bringing it to it. Global models are very good, apparently, very much used in social sciences and medicine when you are looking at average. If you want to see how the average is behaving. Then you're good. But we are not necessarily interested in the average if you do computational material science. We want special cases. But still, one single model to describe the whole population minimizes the overall predictive error, that is the root mean square error. And it's not only that we optimize the root mean square error, but we also have a regularization. Regularization, in fact, means, as I said, it helps us to getting a smooth curve. It also means we do not request that our fitted curve goes exactly through all the points. We just said it should go as good as possible through all the points under the condition that we have a smooth function. Therefore, obviously, a global model disregards on purpose all the local details. It gives a fit, but describes all the local details. Methods which are doing this thing are kernel-rich regression, support vector machines, deep learning, decision trees, and so on. These models are really great if you're interested in a global description, if you're interested in the average behavior of big numbers. However, they are not really necessarily helpful for deeper insight, and it's not really what we typically need in material science. So coming back to this example here, global models, as you have seen it before, fitted to the entire data set may be difficult to interpret. That may well hide or in fact incorrectly describe the true physics which is behind that. So what we think is one aspect we have to do, we should look, are there maybe certain systems which are different? Are there systems which are statistically different? Or are there subgroups which are statistically exceptional? Now, because of time, I'm really simplifying what I'm doing now. It's actually a little bit more complicated. I tell you it also in a moment. So, in fact, if you look at this data, you could say, actually, maybe I should not fit everything. Maybe, in fact, the systems here and the first systems there should be treated independently. I mean, maybe actually they have a certain type of behavior. And so if you could do this in a systematic way, identifying are there systems which are exceptional, that would be nice. And this is what we call subgroup discovery. And the key scientists behind this are Gilles Freken and Mario Bolai. And there's another example of what I just have shown, but it's another tutorial. So let's assume that we have, say, material property 1, material property 2, and these are our big data. I mean, just really tutorial examples. We have 6 data. This would be the global model. The best fit of these data would be, as you see it here, with a certain error bar, and this would be the slope would be somewhat your physical understanding. But if you are able to look more into the properties what you know about the data, you may find that maybe actually some data are blue and some data are red. And then in fact you will see there's a subgroup where the understanding should be this one, and there's a subgroup. So it could well be that you have a big data, but the true explanation is really orthogonal to what you had before, because there are subgroups which should be treated independently. And at the end, of course, we want to have some understanding. So the way to do this is a very interesting Boolean type of analysis. What you say, and this is now an iterative process, you say there's something I'm interested in. So you first have to identify your interestingness. Let's say I want a good energy, I want a good transparency, or I want a band gap of, I say, 1.5 electron volts or something. So you define what you want, and then you play in asking what conditions in the data fulfill this criterion. And these conditions you allow to be flexible, and then you determine in an iterative way. So you find conjunctions as a sum of several conditions, C1 and C up to whatever you want. And then we say, are these conjunctions good to maximize a quality function? That means extension of the subgroup, making the subgroup as big as possible, and optimizing the quantity, for example, the band gap which we want to optimize. So are there systems where there are conditions which have these properties? And the C1s are Boolean statements. Boolean statements which are simple to calculate. For example, ionization potentials. Is there a condition that the ionization potential of atom A and the ionization potential of atom B in some type of adding or subtracting is helping us to identify a subgroup? Maybe it's smaller than minus 0.03. These numbers are found in an iterative way. You don't give this. You give the conditions. You say, is this special in these conditions? The numbers are then coming out in the subgroup discovery to identify a certain subgroup. So subgroup discovery aims to look at all the data to find those which are statistically exceptional. And let me just go here. This is done in an iterative process. New measures may require, so a new type of questions which you have may require new algorithms or new methods. Now here's one thing which is very simple. This is an example which we have used at the beginning. If you look at gold clusters of different sizes, and in fact in the molecular dynamics of different structures. If you would not look at them the way I'm plotting it here, if you just say, actually, I'm just have the data points, you would not see much structure. But if you look for exceptions, for statistically exceptional systems, you will, the subgroup discoverer will tell you, you should plot them as a function, band gap as a function of cohesive energy, and then you see one subgroup which is red and one subgroup which is blue. In this case, they even separate from each other. The odd clusters are different to the even clusters. So an odd number of gold atoms are different to the even number of gold atoms. If you're a scientist in condensed matter, it's obvious that this must be a result, but this in fact was just a result of the subgroup discovery. You have a lot of data points, and subgroup discovery tells you these systems, because they have odd number of electrons, they should be metallic. They have an even number, and they could be at least semiconducting. So they should be also treated differently if you want to do this. Now, how to find these conditions? And here I have the example of comparing statistical learning or machine learning to what we have invented or developed, compressed sensing. This is the method which comes from signal processing. It comes from the idea that you have a complex signal in music or in video, and you want to bring the system, you want to see what is the identity, what is the essence of the system. Can I bring this down as much as possible? In principle, it's the same idea what you want to do. In kernel-rich regression, the example we have seen, you write your function as a function of a sum over Gaussians. In compressed sensing, you say the quantity which I want is a linear, is a product of two vectors. A vector which has all the descriptors. D has all the basis functions, all the possibilities which could be good for describing my system. And everything is multiplied with an unknown coefficient. So this is C1 D1 plus C2 D2 and so on. And in fact, this summation which you see here could be long. Several thousand possibilities, and you will see actually could be even trillion of possibilities. And then in the same way, on left and right, you say, I want that my function, which I find hopefully, and the numbers which I know, that this should be minimized. In machine learning, in the traditional way, as we said, you add a regularization term to make a smooth function. Here you also use a regularization term. So the mathematics is really the same. The purpose is a different one. So you could say this is also a type of machine learning. But here you add what is called the norm zero of these coefficients. Now what is the norm zero? The norm zero is a number of known zero elements. So you now solve it not under the condition there should be no noise and it should be smooth. You solve this under the constraint that most of these coefficients should be zero. You want to optimize that the number of non-zero elements is as low as possible. So you have a summation. You said my probability is a function of, is a summation of D1, C1 and whatever, thousands or millions of possibilities. And from these million of coefficients, they should be all zero, except a few ones. So this is what we're solving in compressed sensing in this way. Now this is not so easy because the norm zero sounds very easy. You just count how many elements are not zero, but it's a combinatorial problem if things get big to really evaluate this. And so the way we have first done this is so-called lasso method, least absolute shrinkage and selection operator. This was the first result in 2015. Lasso, in fact, is using an approximation to norm zero. Norm zero approximation, which you can solve easily, is the norm 1. Norm 2 is the one which you know. I mean, the norm 2 is just the length, is the distance between 2 points. Norm 1 is also a distance between 2 points, but the way you would drive in Manhattan. So you want to from here, you have to drive this way. So it's basically another way of distance, which is an approximation to norm 0. And that you can do. But the problem of the lasso is that if your descriptors which you have here are somewhat linear dependent, and that actually may happen. Oh, actually, I need 4 or 5 minutes, I think. Then, then in fact, you run into a problem, and then you come to what is called sure independent screening and sparsifying operator. And this is what we now can do, is you have a sum here which can be 100 billion or can be trillion elements long. And from these trillion elements, this method which we have developed finds the best 2. And that, of course, is then also a possibility to give you some insight. Now, I seem that I'm really talking too much and I'm really have to jump over. I just really want to give you then one example and then I show you a little movie to be really fast. So this is one example which we have done. So this simple example of rock salt to zinc blender, what this method finds from really many trillions of options, it finds a descriptor which you certainly would not find yourself, but everything is built on properties of the free atoms. Is the wave function radius of the B atom, of the S function, the P wave function of atom A, and so on, in some very strange way. I think the function which you find here has no physical meaning. The function is just coming from the way you want to have a map which tells you everything right from the green line is red, namely zinc blended, everything left from the green line is blue, namely rock salt. So you find functions, but of course what is important, I think, that these quantities, these are called the actuators. They are really driving the whole thing. And you see, actually, we get a very good description. And even if you would have left some out, for example, carbon in the diamond structure is very special. The distance is the cohesive energy. We would have predicted that this is a very special situation. Now, I wanted to really describe many other things. I wanted to talk about topological insulators, which I don't do. So the topology, let me only tell you that at least we found a nice map. We found systems which are topological insulators, which are metals, which are semiconductors, and we found some intermediate region which nobody had expected before. We looked at things, and okay, this is my summary slide. Actually, this is one of 3 summary slides. So this is the problem, right? I mean, this is the scientists in material science looking for the needle. And as we all said, already said, actually making the haystack bigger doesn't really necessarily help us. And that is the problem of the regularized root mean square error. We think it's not a good approach, although at the moment we are still doing it because we don't have a better idea. We know the problem. We know how to optimize some things with the scissor approach, bringing down things to really very few parameters, but it's not really yet a solution. But needles are clearly a well-defined subgroup. So if we know what we are looking for, we can use, in fact, the methodology which you just identified to say we should not really look for this thing as the big thing. We should immediately try to identify what type of things are special. Now, of course, you can say the hay is certainly interesting. So why don't I describe the hay and then maybe everything which is not described are the needles. But material science is so flexible. I mean, there are so many things. It's not really just one hay. There's 1,000 different ways of hay. So that's also a too dangerous option to do. So we have looked at many things. I talked to you about crystal structure prediction. We looked at transparent oxides. We looked at perovskites. We looked at topological insulators, at metal insulator, and at heterogeneous catalysis. So this is the website of the NOMAD project, and I just wanted to really play the UQ or YouTube movie because it's really just summarizing all the things which I certainly have not done, unfortunately, but I hope that it's interesting to you, and I hope actually because I was not sure if I really started things correctly.
The NOMAD European Centre of Excellence.
Okay.
Your gateway to material science. This is John, an engineer in sustainable energy field who wants to build the best solar cells ever. And this is Laura, a chemistry researcher who wants to design the most efficient batteries for the next generation
Worked before,
of
but
electric cars. So what did John and Laura have in common? Well, to achieve their objectives, they both need to use...
let me see. This is again the problem of the Bluetooth being switched off, I guess, right?
European Centre of Excellence. Your gateway to material science then. This is John, an engineer in the sustainable energy field who wants to build the best solar cells ever. And this is Laura, a chemistry researcher who wants to design the most efficient batteries for the next generation of electric cars. So what do John and Laura have in common? Well, to achieve their objectives, they both need to use new high-performance materials. So what can material science do for that? The ideal solution would be to provide them with a map of materials where they can identify and select what they need. Indeed, the amount of different possible materials is practically infinite. So what if all materials could be grouped according to their properties and functions? Is this already possible? Well, this is the idea behind NOMAD, the Novel Materials Discovery Laboratory. NOMAD is the European Centre of Excellence for Material Science Data, set up in 2015 to enable the quest for new and novel materials and their properties, and to reveal unknown properties of already known materials. The foundation of this European Centre of Excellence is the database called the NOMAD repository, which is available to all and based on open access principles. It hosts input and output files of all significant computational material science codes for at least 10 years, for free. It also enables a confirmatory analysis of materials data, their reuse and repurposing. As a NOMAD repository includes extremely heterogeneous data, which do not allow for direct comparison, these are being processed into code-independent, machine-readable and standardized form. This is the NOMAD archive, which provides the open access data from the repository in an easy-to-use and easy-to-access way. The archive is the base for the NOMAD encyclopedia, which displays the properties of computed materials based on millions of calculations that have been performed worldwide. Not only does the encyclopedia provide information about known compounds and their known properties, but it also makes it possible to propose a previously unknown material with the desired characteristics for a special application, or to bring to light the previously unknown properties of known materials. The NOMAD COE also provides a set of big data analytics tools that uncover structure and correlations in big data of materials. This enables scientists and engineers to decide which materials are useful for specific applications, or which new materials should be the focus of future studies. As seeing helps understanding, NOMAD is also developing a virtual reality environment to allow for interactive data exploration, training and dissemination. Clearly, all of this is made possible by the underlying NOMAD high-performance computing platform, which consists of a distributed multi-layered storage system connected to scalable computing capacity. Data is the raw material of the 21st century. If you deal with material science, the NOMAD Centre of Excellence is your gateway. Start using it now at nomad-coe.eu.
Okay, starting it now means also, again, this the summary. So the reason for do this, I mean, you have to do all this work and really giving the data, but the idea is, of course, speed up science and really using data from so many people and having millions of possibilities. When data are fair, they can be used for artificial intelligence. This is what I wanted to show you. And of course, do science. This is the thing which we want. But I wanted to also say that we are not only actually using UQ, but we are also having a NOMAD mirror here in China. Actually, we are just building it, I have to say. So colleagues from USTC and Hefei are presently establishing a NOMAD branch, NOMAD CH, actually CN, China is CN, right? Okay, strange. Okay, so CN. What is CH? I forgot.
Switzerland.
Yeah? Oh, so Switzerland. Okay. No, so this NOMAD CN, right? Very important. So this is presently done, and actually helping them to develop it, and then of course also taking part would be very good. And thank you very much for your attention.